So now it's easily seen that your Q, the charge on the capacitor, whose derivative is the current, whose second derivative is what drives the voltage of the inductor, is equal to some Q naught, we'll say. We could use any constant here. I just used Q naught, times e raised to, well, it's e to the mt. M is this, and we probably ought to multiply that by t, which I apparently neglected to do while I was saying this in class, although I don't think that confused anybody any more than they might have already been confused. I'll note that Richard was sitting there following all this along with the textbook, and he never said anything, which would be, you'd think he might. So I did check after class to check my notation against that of the textbook, because there are various ways to rearrange this, and it turns out that the textbook had it right. They did it the way I did it. Okay. Okay, so anyhow, you get two real solutions if this discriminant is positive, repeated real solutions if this discriminant is 0, and complex solutions if the discriminant is less than 0. And these solutions mimic right down the line the solutions that we got for the mechanical system, the harmonic oscillator with a drag coefficient. Okay, now looking at what this implies, let's just see where r squared over 4l squared minus 1 over lc is 0. We rearrange that, multiply it. I multiply through by common denominator, which will be 4l squared c, and we get r squared c minus 4l equals 0. L equals r squared c over 4. Okay, that's the transition of the behavior of the system from the solution where where your discriminant is negative to the solution where your discriminant is positive. Transition from an oscillating behavior to a combination of exponential behaviors. Now, it then follows that r squared over 4l squared minus lc is greater than 0 when? Oh, well, if L is small enough, this is big enough. Well, delay what I just said there, but this occurs if L is less than r squared c over 4. And I'm going to stop and check that, because I want to check this at every point and make sure that I'm not saying something really ignorant. Okay, if I look at this, it's really obvious. If L is big, that's going to make this negative. Okay, but that's going to make this small, so that would be positive. Now, I'm still seeing a contradiction here. Hang on, I'm going to reconcile this. Okay, I've verified it 3 ways. Yeah, you do have an L in the denominator here, which would make this small, but you have an L squared in the denominator here, which would make this much smaller, making this bigger and this relatively smaller. So you would have a positive if you have a small inductance, and that fits with what you would expect. If you don't have much inductance, then your coil maybe only has a loop or two, maybe it has a small area. We didn't really talk about how area affects that because we haven't talked about inductors in detail, but intuitively, a small inductance wouldn't make much difference in the behavior of a circuit. And the behavior of the circuit, of course, we haven't solved the equation to see this, but if L is absent or is small, then the circuit pretty much behaves like an RC circuit with its exponential behavior, and there's no oscillatory behavior. The oscillatory behavior depends on having a large enough value of L. And of course, oscillatory behavior is what occurs when this expression is less than 0, making the square root imaginary. Okay, so if L is big enough, you have oscillatory behavior. If it's small, you have something very much like exponential behavior. Okay, so now there's our detail of the types of solutions. What I want to do is assume that L is greater than R squared C over 4, sufficient to give us oscillatory behavior, and we're going to drive the system, the circuit, with the source V naught sine of omega S t. Now I'm going to stop here and just draw a little picture.